So starting on to our next chapter, we will have six chapter in our syllabus. According to our syllabus, we have six chapter, that is water turbines and pumps. In this chapter, we will study various types of turbines. We will study the classification of the turbines on various aspects and the different types of pumps that are being used to transfer the hydraulic energy and from one point to another point, and the water turbines which are being used to in the hydropower plants to produce electricity. So first of all, let's have a glimpse on the definitions of water pumps and water turbines. So hydraulic machines we have read in the previous chapter also. That is the machines that are either converting the hydraulic energy into the mechanical energy or the mechanical energy to the electric or into the hydraulic energy. So either they are converting the mechanical into hydraulic energy or hydraulic energy into the mechanical energy. They are all called the hydraulic machines. So we have the water turbines and pump, whereas if we have the definitions of the turbines, the machines, turbines क्या कर रही हैं? The turbines are converting the hydraulic energy into the mechanical energy because they are receiving the energy in the form of the water from the higher height to the pen stove. Whenever the water is striking into, onto the blades of the turbine, they are receiving the hydraulic energy, and on the rotation of the turbines, we are generating the mechanical energy. And then that mechanical energy is being converted into the electrical energy with the help of the dynamo, which is being attached with the turbines. So turbines are basically receiving the hydraulic energy, that is, they are converting the hydraulic energy into the mechanical energy. Whereas the water pumps are receiving the mechanical energy, that is, as soon as you switch on the electrical power from the electrical source, they are start rotating or reciprocating, so that is generally producing the mechanical energy. So as soon as the mechanical energy they are switched on, they are start converting the mechanical energy into hydraulic energy because by using the water pumps you are generating the hydraulic energy so that you can transport the water from one point to another point, whether you are increasing the pressure of the water or whether you are increasing the potential energy. How you are increasing the potential energy? That is, if you are transporting the water from the lower level to the higher level or from higher level to the lower level. That is, you are increasing the potential energy or you are transporting the water from the one level to another level with the increase in the pressure energy. So basically, you are converting the mechanical energy into the hydraulic energy with the help of the water pumps. You all know that you have water pumps in your homes also. You have submersible pumps. You have simple water pump also to transport the water at the water tank which is situated at the top of your home. You are running the submersible motor or you are running the simple water pump so that you can transport the water from the lower ground level from the to the high point or the highest point where the water tank is being situated. That is, you are increasing the hydraulic energy of the water. So that is why water pump is called a machine, a hydraulic machine which is converting the mechanical energy into the hydraulic energy. Whereas the turbines are receiving the hydraulic energy and they are converting the hydraulic energy into the mechanical energy, which is being further converted into electrical energy with the help of the dynamo which are being installed at the, after the turbines in the hydropower plants. So this is basically differentiate turbines with the water pumps. That is, there is only a difference between the conversion of the energy. Both are receiving one form of energy and converting that form into the another form, and they are also vice versa to each other. That is, turbines are receiving hydraulic and converting it into the mechanical energy, whereas water pumps are receiving mechanical energy and they are converting that mechanical energy into the hydraulic energy. So let's have a common or a simple example of a water turbine. You can see in the figure also. We have a dam here, and this is the highest point that is called the head race, from where at where the water is being stored, and this is being transported through a large duct pipe that is called penstock from a high height of the dam to the lower point of the turbine. So this is a turbine which is having some vanes. You may sometimes also call it blades. So this is the turbine. You can see we have installed a nozzle at the end of the penstock so as to increase the energy. So that is why you can see here we have installed a converging nozzle. That is, the diameter at the outlet of the nozzle is less than as compared to the diameter at the inlet. So diameter at the inlet of the nozzle is equal to the outer diameter of the penstock. So here we have installed a converging nozzle. So that converging nozzle is converting whole amount of pressure and tension energy into the single form of energy that is called the kinetic energy. So whenever the water is being falling from the or it is being transported from the dam using the pen stroke at the end of the nozzle, we have installed a emerging nozzle at the end of the pen stroke, and whole of the energy is being generated the kinetic energy. And whenever the hydraulic energy, which is in the form of kinetic energy, is being striking the waves of the turbines, it starts rotating. As soon as it starts rotating, it will generate the mechanical energy. So as soon as it is generating mechanical energy, then further we have the installed a dynamo which is receiving the mechanical energy and it's converting that mechanical energy into the electrical energy. Then that electrical energy is being transmitted in the various parts of the domestic as well as the commercial areas. So this is the head race. This point is called the head race. That is the highest point from where the water is being stored at the highest point of the dam. So this is the dam. This is the gross head you can see, and this is the tail race. So what is tail race? The amount of water that is being transported onto the oil, striking the vanes of the turbine. The amount of water that is being left is being stored with the help of the fan stove. And we have in the further chapter we will study that there is one draft tube through which we are transporting that water from the leftover water from the which is being striking the vanes of the turbine. After that, it will be supplied through the draft tube again to the head race, or you can say again to the point from where it is again reusable to transmitting from the higher height to the point where it is being used to striking the vanes of the turbine. So this is the turbine is basically a machine which is using the air. You can see this is using the kinetic energy of the fluids and transforming that kinetic energy that is the form of the hydraulic energy. Is converting that or transforming that kinetic energy into the mechanical energy through this mechanism. As soon as you can see, there are a number of blades or number of vanes are being installed on the rotor of the turbine, and it is being used to produce the mechanical energy. As soon as the water is striking on the vanes of the turbine, it starts rotating, and as soon as it starts rotating, it will generate the mechanical energy. And then that mechanical energy is again being used to convert the electrical energy with the help of the generator or the dynamo that is being installed at the end of the turbine. So this gross head is what this is the difference between the tail race or the point where the water is being used to transport from the upper height of the dam. So this difference is called the gross head. That is difference between the head race and the tail race is called the head, gross head. So this is called the gross head, and net head is what the amount of water or the amount of head or amount of energy that is available at the inlet of the pipe or inlet of the nozzle. So in outlet of nozzle पे जो मिल रही है और inlet of shaft पे मिल रही है, किसकी shaft पे मिल रही है? The inlet of turbine मिल रही है. That is outlet of shaft पे जितनी energy मिल रही है और हमें जितनी turbine के inlet पे मिल रही है, that energy is called the net head. That is the head available at the outlet of nozzle or at the inlet of the shaft of the turbine. So that is called the net head. So this pipe through which the water is being transported from the from the head stroke to the uh, nozzle, that is called the fan stroke, which is a large diameter pipe through which the water is being transported. So here we have read in the previous chapter also, here we have installed a such tank so that there will be no chances of water handling or knocking in between the fan stroke, and there will be no corrosion or wear and tear of the fan stroke. So we may have installed a such tank here so that all the pressure energy that is being produced so that the pressure waves must be die out in between the fan stroke so that it will not corrode from inside or inner surface of the fan stroke. So there are some definitions I have told you also. This is the gross head, that is the difference between the head race level and the tail race level, where when the water is not flowing from one point to another point. Next is the net head, that is it is defined as the head available at the inlet of the turbine, or you can say the head available at the outlet of the nozzle. So inlet of turbine means that is the head which is being used to rotate the blades of the turbine, or you can say that is available at the outlet of the nozzle. Next are the some efficiency of the turbines. So what are the efficiencies? We can measure the efficiency of turbine in four ways, that is hydraulic efficiency, mechanical efficiency, volumetric efficiency, and then overall efficiency. These are the definitions of the hydraulic, mechanical, and the volumetric and the overall efficiency. For the case of the hydraulic efficiency, we are taking the power developed by the runner of the turbine to the power supplied by the water at the inlet of the turbine. So uh, how much is the hydraulic efficiency? How we are calculating that? It is calculated as that we are taking the power developed by the runner, that is the amount of power that is being generated by the turbine after being producing the mechanical energy divided by the amount of power that is available at the inlet of turbine. You always know that there are some losses in the total head that is being receiving at the inlet of the turbine. So that efficiency is always be less than 100%. You always know that there will be no machine in the universe that is producing 100% efficiency. That is, we are receiving uh, always receiving less than efficiency as that of the 100% in any machine. So the power developed at the node is always less than 100%, so it is placed at the numerator of the ratio, and the power available at the end of the turbine is placed at the denominator. So this efficiency is called the hydraulic efficiency. So mechanical efficiency was that is the ratio of the power that is available at the shaft of the turbine to the power supplied by the power developed by the runner of the turbine. So the power at the shaft of turbine कितनी है और power developed कितनी हो रही है उससे that is what that is called the mechanical efficiency. That is which amount of energy is being produced. That is how much the mechanical energy is being produced by rotating the turbine to the hydraulic energy. That is called the mechanical efficiency. Next is the volumetric efficiency. That is how much is the volume of water actually striking the water, striking the runner to the volume of water supplied to the turbine. Let us say we are supplying a 2000 liter of volume of water at the from the pen stroke, and actual water that is being striking the vanes of the uh, turbine is always less than the amount of being supplied from the pen stroke. So that is the volume of the liquid, volume of the water that is actually striking the veins to the volume of water that is actually available at the inlet of the turbine. That is called the volumetric efficiency. Next is the overall efficiency. That is, it is defined as the ratio of power available at the shaft of turbine to the power supplied by the water at the inlet of turbine. कितनी पावर हमें शाफ्ट के इनलेट पे अवेलेबल है और कितनी हमने सप्लाई की थ्रू द वाटर एट द इनलेट ऑफ द टरबाइन. That is called the overall efficiency. All these efficiencies are denoted by eta to the superscript of their first letter of their name. That is, if we will call it as a hydraulic efficiency, it is denoted by eta h. If we are denoting mechanical efficiency, it is denoted by eta m. If we are denoting volumetric efficiency, it is denoted by eta v. So this type of n is called basically eta, that is eta, and the last one, that is overall efficiency, is being denoted by eta naught, that is eta o. Next is the classification of the hydraulic turbine. That is how we are classifying hydraulic turbine. These are being classified on the basis of the type of energy which is being available at the inlet, the type of uh, direction of flow to the runner. We are getting the classification on the basis of head available at the inlet of turbine, onto the specific speed of the turbine, onto the head of the turbine, or according to the inventor who has invented that particular turbine. So we have certain kinds of classifications of the water turbines or the hydraulic turbines. First is the type of the that is we are classifying the hydraulic turbines on the basis of energy that is available at the inlet of turbine. Let's say first is the impulse turbine and second is the reaction turbine. So what is impulse turbine? You can understand from this figure also. So this is the impulse turbine. You can see we have installed a nozzle at the outlet of the fan stove, and as soon as we are have installed a nozzle at the outlet of the fan stove, we are converting whole amount of energy into the kinetic energy. That is, we are only getting a single form of energy at the inlet of turbine. That is, when we have installed a nozzle, the whole of the energy is being converted into the kinetic energy because we are increasing the velocity of the outlet, but we are increasing the pressure as well as the potential energy are being died out at that point. At the outer of the turbine or at the outer of the this converting nozzle, we are only getting the kinetic energy. So a turbine at in which we are getting at the inlet of turbine, we are getting only the kinetic energy at the inlet of turbine, that turbine is called the impulse turbine. But whereas if you are not installing a nozzle at the end of the fan stroke, you are only getting the pressure energy as well as the kinetic energy at the inlet of turbine, then that turbine is known as the reaction turbine. If you are getting only the if you are only getting the kinetic energy at the inlet of turbine by installing the nozzle at the inlet of the turbine, then it is called the impulse turbine. That is, in the case of the impulse turbine, you can say you are only getting the kinetic energy at the inlet of the turbine. But in the case of the reaction turbine, we don't install any nozzle at the outlet of the turbine, but due to the uninstallation or due to the non-installation of the nozzle at the inlet of the turbine or at the outlet of the fan stove, you are not converting the kinetic energy into kinetic energy. So you're getting a hydraulic energy in the form of pressure energy as well as the kinetic energy. So in the case of the reaction turbine, there are two kinds of energies that are striking the vanes of the turbine. First is the kinetic energy and second is the pressure energy. Whereas in the case of the impulse turbine, we are only getting the kinetic energy at the inlet of turbine. Second is the how you're classifying the hydraulic turbine. Second is according to the direction of flow through the runner. That is how the water is being flowing from the runner. So first is the tangential flow. So in this figure we can see, so this is the water is striking along the tangent of that runner. So what is runner? That is the central portion of the turbine where the shaft is being rotating. So this is called the runner. This central portion is called the runner. That is being installed on the shaft. So as soon as the water is being striking along a tangent, so you must have read the tangent or the diameter or the radius in the trigonometry or the mathematics. So this is the tangent. So the water is being striking along the tangent of the turbine. So this is called tangential flow turbine. Second is the radial flow turbine. If the water is striking along the radius of the turbine or along the radius of the runner, that is called the radial flow turbine. Next is the axial flow turbine. What is axial flow turbine? That is if the water is striking along the axis of the turbine, that is perpendicular to the axis of the turbine. If the position of the penstock is such that the water is being striking along the axis of the turbine or axis of the runner, then it is called the axial flow turbine. Next is the mixed flow turbine. In the case of the mixed flow turbine, we are receiving the water at the inlet of the turbine in the form of the radial flow, and the water is leaving through the axis of the turbine. That is water entering through the radius of the turbine or radius of the runner, and it is leaving along the axis of the turbine. So this is called a mixed flow. In the mixed flow, we have a combination of radial flow as well as the axial flow. That is, um, at the entry, it is entering along the runner of the turbine through the radius of the turbine, and it is leaving through the axis of the runner. So if you are classifying the turbine, so you can see we have a turbine in the form of two forms, that is impulse turbine as well as a reaction turbine. So impulse turbine is basically the scientists who have invented the impulse turbine is the Pelton. So the example of the impulse turbine is a Pelton turbine, and whereas we can classify the reaction turbine in two ways, that is Francis turbine as well as a Kaplan turbine. We study here so Pelton, Francis, and Kaplan. These were the three scientists who have invented these uh, turbines. So first one is the Pelton wheel turbine, second is the Francis turbine, and third is the Kaplan turbine. Whereas Pelton wheel turbine is the impulse turbine. That is, this is the Pelton wheel turbine where we are getting only the kinetic energy at the inlet of the turbine. Whereas in the case of the reaction turbine or in the case of the Francis and Kaplan turbine, we are getting the sum of pressure energy as well as kinetic energy at the inlet of the turbine because we have not installed any nozzle at the outlet of the fan stream. Next classification is according to the head of the at the inlet of the turbine. That is how we are classifying the turbine according to the head. That is, if the head available at the inlet is high head, low head, or the medium head. So if the head available at the inlet of the turbine is high, then it is called high head turbine. If it is available at medium head, it is called the medium head turbine. And if we are not getting the high head or medium head at the inlet of the turbine, that is called the low head turbine. You can also classify the turbine on the basis of the specific speed. That is, if the speed of the turbine is low, medium, or high, then we call it as a low specific speed, medium specific speed, and the high specific speed turbine as per the classifications respectively. Next is the comparison between the reaction turbine as well as the impulse turbine. How you are, this is the most important question as per the syllabus or as per the exam point of view. So how you will differentiate between impulse turbine as well as the reaction turbine. First main difference I have told you that is the difference is that if we are getting the amount of energy only a single form of either at the inlet of turbine or inlet of runner, that is called the kinetic energy, by installing the nozzle at the outlet of the construct, that is called the impulse turbine. But if we are getting the energy in in the sum of pressure energy as well as kinetic energy at the inlet of the runner, that is called the reaction turbine. And also, the steam impinges on the vanes in the form of the kinetic energy, whereas the streamlines are guided along the vanes in the pressure energy and the kinetic energy in the case of the reaction turbine. Blades are symmetrical for the impulse turbine, but blades are designed unsymmetrical for the reaction turbines. And you can see if we are getting only the kinetic energy at the end of the turbine, the blades uh, are being impinged by the water at a high velocity because we have installed a nozzle, converting nozzle at the outlet of the construct. But uh, in the case of the reaction turbine, the steam always flows through the guiding mechanism and then through the moving blade. So it is not impinging or striking at very high velocity because it has some pressure energy also, because we are getting the sum of pressure energy as well as kinetic energy at the inlet of turbine. So we are not getting only the single kinetic energy as in the case of the impulse turbine. Also, the steam or may not be emitted over the whole circumference. Whereas in the case of the reaction turbine, we are getting the steam pressure that is being reduced during the flow through the blades. So the pressure has been reduced for the flow during the rotation of the turbine in the case of the reaction turbine, but the steam may or may not be emitted over the whole circumference in the case of the impulse turbine. So next, in tomorrow's lecture, we will do the working of each and every